In supervised machine learning, we provide labeled data to the computer. For example, if we want to train a model to distinguish between positive and negative customer reviews, we could get a dataset of 100,000 customer reviews and manually label them as either positive or negative. The computer will then use these labels and learn how to categorize new unseen reviews as positive or negative. The drawback to this approach is that it's expensive to label data. If categorizing one review costs 30 cents, we must pay that person $30,000 to classify the entire training dataset. Categorizing a review is fairly simple. Can you imagine how much more expensive it would be to sort articles, or novels, and medical records? It wouldn't cost 30 cents, but probably $30 or more. So going through 100,000 data points would cost north of $3 million. Therefore, we can conclude that supervised learning has significant limitations in terms of scalability. The cost increases exponentially with the complexity of the data fed into the model. People often say ChatGPT has virtually read the entire internet. Can you imagine how much labor would be needed to read and categorize the entire web? How biased would the categorizations be if made by just a few individuals? So, large language models need a slightly different approach. The other obvious option is unsupervised learning. This type of ML operates without labels, seeking to discern the data's underlying structure without direct performance feedback. But with this approach, there isn't a clear objective. Without a specific goal, it's challenging for the model to learn structures that help it understand or generate human language. Moreover, language is a form of expression in which context matters significantly. Words in a single sentence can create context, and each paragraph builds upon the last to enhance it further. Unsupervised learning does not prioritize predicting the next word from previous contexts, potentially overlooking essential language nuances. So, we need a balanced approach, an ML system that scales and self-learns, predicts contextually, and autonomously generates labels. The self-supervised learning approach was the breakthrough that led to the creation of LLMs. It analyzes text databases, automatically generates labels, and predicts subsequent content based on contextual cues from surrounding words. This hybrid approach allowed for the creation of models like ChatGPT and improved their ability to understand and generate language in a natural and aware way. Our next lesson addresses the gradual progress of language models that led to the transformers architecture. This other key innovation allowed AI researchers to work with massive amounts of unlabeled text data. Earlier, we discussed the incredible evolution of language models, from statistical modeling and basic tasks to advanced neural networks and LLMs. In this lesson, I would like to explore the world of language modeling more, adding technical detail to the picture. This will help improve our overall understanding. We'll describe 4 core techniques used for language modeling throughout the years, and how each solved the preceding issues. The first technique, n-grams, is a fundamental building block for language modeling. The idea behind n-grams is pretty simple. We can estimate a word's probability based on the preceding n-1 words. So, in an n-gram with n equal to 1, called a unigram, 1 minus 1 would equal 0, right? This means that the prediction is not based on any context. Let's see how this works. We have the following sentence, and aim to predict the final word. The n-gram model functions by not using any words from "my favorite sport is" to predict basketball. Instead, it would review the entire text and look for the word that appears most often, assuming that the word with the highest frequency is the best bet to fill the blank space in the sentence. So, the unigram model might predict common words like the or and, regardless of their actual fit with the previous words in the sentence. But if n equals 2, called a bigram, the prediction of basketball depends solely on the previous one word. In My Favorite Sport Is, we focus on is to analyze the frequency of all subsequent words in the training data. The same goes for a trigram. The model analyzes instances of sport is in the training data to predict the most frequently occurring subsequent word. So this is how ngram works. Far from ideal, huh? The model seems to miss the subtleties of context and prior information. It simply aims to optimize predictions based on appearance frequencies in the training data. Neural nets are undoubtedly a giant leap forward. Recurrent neural networks, or RNNs, are neural networks that work best with text. A key strength of RNNs is their ability to retain information from prior steps in the neural network. Analyzing previous words in a sentence helps the RNN network decide on the next word. This is a considerable breakthrough compared to ngram models because the order and context of data points are crucial when dealing with language. The primary challenge with RNNs is their difficulty in handling large texts, as they tend to lose earlier information with progressive text segments. This problem is called the vanishing gradient issue. To solve this, AI scientists developed long short-term memory, or LSTM networks. LSTMs improved traditional RNN models by introducing a gate architecture to choose which information to retain and which to discard. This allows the network to keep important long-term information and forget irrelevant data, which makes LSTMs significantly better at tasks involving complex text data. The main drawback of LSTMs is their high computational cost and slow training speed on large datasets, making them unscalable. But in 2017, the paper Attention is All You Need introduced the concept of transformers and the attention mechanism. The attention mechanism allows a model to assess the significance of various words or parts of words or tokens in an input sequence to generate an output. Therefore, the model identifies key words and focuses more intensely, lowering computational costs and enhancing scalability. Transformers process text by selectively focusing on relevant sequence parts at each step, rather than handling the entire text simultaneously. This is achieved by assigning an attention score to each word in the input sequence. Words with higher attention scores are deemed more significant, enabling transformers to handle long-range dependencies. Okay, great. So now you know how we got the technology that made the creation of LLMs like ChatGPT possible. We're making excellent progress. We'll discuss the different stages when building a large language model, including model design, dataset engineering, pre-training, preliminary evaluation, post-training, fine-tuning, and final testing and evaluation. These stages are not always strictly sequential in a real-world environment and could sometimes overlap. Nevertheless, using this representation would make it much easier to illustrate and explain the LLM creation process. The initial phase we discussed, model design, involves AI strategists and developers selecting the neural network architecture to employ. For example, they might choose transformers, CNNs, RNNs, etc. Additionally, they must decide on the model's depth, number of layers in the neural network, and the total parameters it will contain. The architecture choices at this stage will determine the scope of work and what the model can and cannot do. There's a popular saying among data practitioners that a model is only as good as the data used to build it. Undoubtedly, the dataset engineering phase is crucial, involving the collection, cleansing, and structuring of training data for the model. There are two main ways to acquire data to build an AI model: scrape publicly available data from the internet, or use proprietary data. But few companies possess enough data to build an LLM with proprietary data only. Many AI strategists, like Bernard Marr, agree that the companies that own the most proprietary data will likely have a competitive advantage when building AI systems. It's essential for AI developers engaged in dataset engineering to consider key ethical issues, including data diversity and building datasets that address various biases. Once these preparations are complete, the pre-training phase begins, involving training the model on a large corpus of raw data from the dataset engineering phase. During pre-training, we obtain a raw version of the model. But, depending on the pre-training data, the model could provide undesired outputs. For example, if we trained it with Internet forum data, the model could provide output responses containing offensive language and different biases. Moreover, we might be building a model that will be used for a specific domain. And when a model trained on general data needs to be used in a specific industry, we need to adapt its outputs to meet the specialized requirements of the field. Suppose you're working on a customer support chatbot. In that case, you want to train the chatbot to reply in a customer-friendly way that corresponds to client expectations and the service they use when talking to human customer support personnel. So, AI developers evaluate the preliminary performance of the model and gain an idea of its capabilities. Once they understand what needs to be improved, they'll address these issues in the post-training phase. Post-training consists of two steps. First, AI developers use supervised fine-tuning with high-quality data to improve the pre-trained model. In the second step, they'll refine the model by incorporating human feedback, like annotations. The next phase of model development, fine-tuning, updates the model's weights to enhance its quality and speed. For example, by changing weights, we can make a model smaller and faster, better suited for a specific task, and less capable in general performance. Lastly, in the final phase, we again test and evaluate the model. This time, we are much stricter and want to put ourselves in the end user's shoes. We aim to evaluate the model's response quality, accuracy, speed, and, crucially, its ethical behavior. In the next section of the course, we'll discuss model evaluation and how it's performed in practice. Right. I want to summarize 3 crucial Gen AI concepts in this lesson. Clarifying these terms with an easy-to-understand example is helpful because people often use them interchangeably, even though they describe different activities. You might often hear, "We'll fine-tune the model," or "We'll use prompt engineering to improve the model's performance." Typically, they refer to one of 3 distinct methods: prompt engineering, RAG, or fine-tuning. All 3 techniques enhance an LLM's response accuracy and effectiveness in specific scenarios by targeting different aspects of AI functionality. Prompt engineering is when we explain to the model how to behave or what context to consider. We don't change any of its weights or add new data. We use instructions and provide verbal examples, explaining the desired output we want to obtain. This is fairly easy to do, and the best part is that we can consistently refine our prompts through multiple iterations to achieve satisfactory AI outputs. It's important to note that the model doesn't change. It merely adapts to our verbal instructions. Retrieval-Augmented Generation, or RAG, is another technique that doesn't change the model's weights. With RAG, we attach a database to the model, which can be used as a library for expanded context. This method provides significantly more examples of how the model can be used to learn to perform optimally. RAG and prompt engineering are effective, but making an LLM smarter or faster is unlikely without modifying its weight. This complex task requires additional training for an already trained model. This process is known as fine-tuning. Sometimes extra data is required to conduct fine-tuning. Moreover, fine-tuning can be computationally expensive, and we can't use an iterative process like prompt engineering and adding RAG. Let me explain an example that will clarify matters further. Since GPT's introduction, our team has been eager to explore products utilizing an LLM. We eventually developed an interview simulator based on the GPT engine. If we were to retrain the GPT model and assign it new weights to make it lighter and faster to give responses to users quicker, this would have been fine-tuning. We couldn't do that because OpenAI's fine-tuning was an experimental program inaccessible to all developers during the tool's construction. But even if it was available, it doesn't fit our use case because we want to create an interview bot that can generalize well and adapt to the changing circumstances during an interview. We aimed to enhance the model by integrating a database of sample interview questions, providing context for tailored queries based on the user's selected interview type. This led to the incorporation of RAG, with multiple adjustments made to the database during the app's development based on the model's performance. The prompt engineering phase was the most time-consuming. We had to instruct the model on displaying code questions, the types of queries for various interview stages, evaluating students afterward, the communication tone, following up on responses, and other aspects. This project indeed showed us the rising importance of prompt engineering skills and the multiple back-and-forth iterations necessary to build an AI product that behaves as expected. I hope this example clearly illustrates fine-tuning, RAG, and prompt engineering. Until recently, the machine learning models developed by companies were limited to narrow applications. Image recognition models were trained to excel at identifying objects within images. Speech recognition systems specialized in converting spoken language into written text. NLP models dealt with narrow language tasks such as sentiment analysis or translation. Time series models were used to predict stock prices, market volatility, etc. All these models excelled in a very narrow range of tasks. The introduction of large language models led to a significant transition over the last few years. LLM's complex and sophisticated structure, trained on massive data, allows them to excel in general-purpose tasks. LLM's capabilities are not confined to one or two types of tasks, or are within a single domain. Instead, with some fine-tuning and prompt engineering, LLMs can perform well in many fields. At first, LLMs were purely text-to-text models, generating responses based solely on textual input and output. But it wasn't long before they could work with code and different types of files, such as Excel and PDF, and even read the information in images and videos. Many were surprised by how fast this technology progressed. The point at which LLMs evolved from mere text-to-text frameworks to generating text, code, images, and video marked their transition from strictly language models to more sophisticated multimodal systems. The correct term the AI community used to refer to them is foundation models. This name comes from the idea that these models serve as a foundational layer for various applications across multiple disciplines. Foundation models are enormous, can perform various tasks, and are immensely powerful. According to OpenAI's Sam Altman, few organizations will be capable of building their own foundation models in the future. Big tech firms want to compete in this market, and several governments may wish to create their own foundation model. Everyone else will either build their application-specific in-house models or build on top of the foundation models created by big tech. Or the open-source community may rise to the occasion and prove big tech executives wrong. One of the eternal dilemmas in the business world is known as buy versus make. This decision determines whether to outsource specific company processes or retain them internally. The golden rule MBA graduates are taught is that a company should try to retain internally all strategic value-adding activities because they are essential for the business. In turn, management can externally delegate non-core activities aimed at efficiency. All of that's great. But when discussing AI and large language models, the situation is unique. As we previously mentioned, few companies and organizations worldwide will be able to build their own foundation models. Creating these models is costly, and few businesses can achieve the necessary scale. Most companies face a critical choice: either build on an existing foundation model or develop their own version from an open-source model. In many cases, firms lack the expertise and resources to train a custom model, yet they recognize AI as a core value add to their business. Consequently, these businesses must rely on organizations like OpenAI, which offer access to foundational models like GPT through a model-as-service arrangement. So, you see the contradiction, right? AI can be a core value-generating aspect of the business, but AI availability and development don't fully depend on a company's in-house efforts. So, how would regular businesses compete with each other if everyone could use OpenAI's API and gain access to some of the world's most advanced AI models with a single API call? In this scenario, the ability to adapt AI to specific use cases will be an actual differentiating factor. The expertise of in-house AI engineers in prompt engineering, RAG, and fine-tuning will help many businesses gain an edge over competitors. Consequently, the demand for skilled AI engineers is expected to surge in the near future. These fascinating developments indicate a significant paradigm shift that will continue.